the recording. Okay. Good evening once again. Are you able to hear me? Should I continue? Hello, are you guys able to hear me?
We can hear you.
Okay, thank you so much. Are you also able to see the projection?
Yes.
Okay, thank you so much. We are looking at its chapter. The document is written chapter 8. In other books, it's chapter 8, but in other ones, it's chapter 10. So don't be confused when you see the title of the document being chapter 10, but the contents say it's chapter 8. So this chapter is a continuation of hypothesis test. Remember, we did hypothesis test for T distribution, for Z distribution, for F distribution, and now we are looking at the one for chi-square distribution. We are looking at the continuation of hypothesis, but our focus today is on chi-squared test. And this one is the most simplest chapter ever, but you can only master it if you understand the basics. Just like I used to do with other chapters, I am going to introduce you to the basics because my experience, or let me just say experience, has taught me that introducing my students to the basics makes them more prepared to respond to the questions they are asked in the assessment. So what I know is that if I take you through the basics first, you will be able to respond to the questions that we are going to look into tonight. So before I'm going to join in using the other device where I'm going to be able to write, let us get down to the nitty-gritty. So we are moving on to slide number 2. I'm going to skip this slide number 2. I will go to slide number 3. You will read slide number 2 on your own. So what is important is what you see on this slide. So what you have to know is that there are 2 techniques that are involved in chi-squared tests. There are 2 techniques that we are going to use in tackling all the problems pertaining to a chi-squared test. The first technique is goodness of fit. But before I get down to deeper details of these ones, I have to reiterate that they won't tell you that here you are using the goodness of fit or here you are using the contingency table. They won't tell you that. Just like with T distribution and Z distribution, they were not telling you that here you are using Z, here you are using T. You had to know the conditions for using either T or Z. So even in this chapter, you have to know the conditions for using the goodness of fit test. You also have to know the conditions for using contingency table. They are not going to tell you that here you are using goodness of fit or you are using contingency table. Are we together?
Yes, we are.
Okay. So when it comes to the goodness of fit, this goodness of fit test is applied to the data that is produced by a multinomial experiment. So when we talk about multinomial experiment, we talk about that experiment that involves the word multi, the prefix multi here. The prefix multi here means many. Remember, we had one of the distributions of probability was binomial, if your mind serves you well. So with binomial distribution, we said the prefix bi means two. Nomial means number. So meaning that we are dealing with two numbers. So the binomial experiment is the one that deals with two numbers. So multinomial experiment, multi means many. The prefix multi means many. Nomial means numbers or number. So when we talk about multinomial experiment, we talk about that experiment which involves many numbers. Specifically, we will be looking at the values of n and not the values of n, but the values of p, which are the proportions. You will see when we tackle the problem pertinent to goodness of fit that you will be given more than one or more than two p's. So you'll be having three or more p's, and that follows multinomial experiment. You will understand when I start writing the condition. What you have to know here is that there are two conditions. There are two techniques that are involved in the chi-squared test. And the first technique is a goodness of fit, which is used when we are dealing with multinomial experiment. And the second one is a contingency table, which is used to test for statistical independence of the events or of the variables. Let me repeat this one, but I'm still going to write when I join the session using my other device. We are saying that in this chapter, we will be using two techniques to analyze data. The first technique is goodness of fit. We use goodness of fit when we are dealing with a multinomial experiment. And then secondly, the second technique is contingency table. We use contingency table when we are testing for statistical independence of the variables or of the events. Are we together?
Yes.
Yeah.
Okay. So let me now, let me see if it's necessary for me to go to the next slide. Okay. I don't think it would be necessary for now. How many slides do we have? They are 33 and we are gonna cover them before 12 o'clock. So I'm going to summarize all these slides in less than 2 hours. So let me see. I want to join the session using this other device. Any question while we are still waiting for this device to respond? Do you have questions, comment?
No, we don't have questions.
Okay. Please do not read what you see on the screen in case something comes up, because I'm using my phone now and not a PC. I am migrating to the phone, but I will be logged in using in both the devices. Okay, I hope you are able to see the projection because I can see it from my side.
Yes, we can see.
Okay, thank you. Remember, how many techniques do we have in chi-squared? And name them. What is the first technique?
Goodness of fit, test, contingency table.
Good, you are ready. Then the goodness of fit and the contingency table. So these are the two techniques. So here, make sure you take notes because I am giving you the basics. So once you master these basics, just like we did in the previous chapters, just know you will be the master of this chapter. I know when your lecturers are going to teach you, those who are being taught by Ms. Mulaute and Ms. Power, when they are going to teach you, probably next week, of course it's next week, you will be confused. But given this information that I'm giving you now, you won't be confused. So make sure that you take note of everything I say here. If you don't understand, feel free to ask me. Then I will be able to clarify so that you don't swim in confusion. So, under the goodness of fit, the first thing that you have to know is that we said for goodness of fit, we will be doing what? We'll be dealing with a multinomial experiment. This is X. Multinomial experiment. That is the goodness of fit. We use it when we are dealing with a multinomial experiment. That is the first thing that you have to know. Second, under the contingency table, what are we dealing with? This is where we'll be testing for statistical independence of variables. With the goodness of fit, we are dealing with multinomial experiment, and normally the test here under the goodness of fit, we will be checking whether there is a change or not. So with the goodness of fit, we are dealing with a multinomial experiment wherein the test will be based on whether there is a change in the proportions or not, or there is a difference in the proportion or not. Whereas under contingency table, the test will be based on the statistical independence of variables. That is the first difference between the goodness of fit and the contingency table. And this first condition is very important because it is key to all these other conditions that I'm going to introduce you to. But all of them are important. Yet this first one is the most important as it's gonna come from the question. You will see when I start projecting the question. What you should know is that with the goodness of fit, we are dealing with a multinomial experiment wherein we are testing whether there is a change or not, or whether there is a difference or not. And then under the second technique, which is a contingency table, we are testing for the statistical independence of variables. We want to check if you want to make this more clear to you, under the contingency table, you can say, here we want to check if one variable affects the other. So that's another thing that you have to know when they say we are testing for statistical independence of variables. Are we together? Under the goodness of fit, we are testing whether there is a change or not. Change is the same as difference because you know, I will show you, I will use a practical example so that you can see what I mean when I say a change is the same as the difference. And then the contingency table is used to test for statistical independence of variables, wherein we are saying, does one variable affect the outcome of the other or what? So that will be the contingency table. You will understand more when we expatiate on this. Does it make sense up to so far? Can I move on to the second condition?
Yes.
Okay. Make sure you write them because once I start presenting using the PC, this screen that you see now is going to disappear and then you will see the one for PC. Note that GOF stands for goodness of fit. GOF is goodness of fit. I don't want to write it in full, or let me just try to write it. Goodness of fit, and then this side, you will have contingency table. So now the second condition for both of them is that when we denote H naught for this one, it will always be like, and I said always, it will, your H naught will always be like P1 equals A1 semicolon, P2 equals A2 semicolon, PK equals AK. And what this means is that there is no change in brackets or no difference. Because if P1 equals A1, it means there is no change. They are still the same. So obviously, the alternative will be, it will always be like at least one PI is not equal to its specified value. So H naught will always be like P1 equals A1, P2 equals A2, PK equals AK. I will explain what that means. And then H1 implies that at least one PI is not equal to its specified value. Yeah, working online is really challenging because now I don't have enough space here. And I wanted to write in brackets what it implies. So what is the opposite of no change?
Change.
Remember, if the noun says there is no change, the alternative will say?
There is change.
Good. So it means that here, because you have a space, you will write in brackets. After writing at least one PI is not equal to its specified value, you will write there is a change or there is a difference. Are we together? You will write in brackets here after this statement, there is a change or there is a difference. Are we together? So Another thing that I have to clarify here is that this P1 equals A1. They are just the numbers that you know. So you will be given different proportions. So if, say for instance, your proportion number 1 is 50%, so you will say P1 equals, where you see A1, this A1, A2, AK denotes the percentages or the proportions or the probabilities. You will write the numbers here. So if proportion number 1 equals 50%, you will write 0.5 here instead of A1. You will say P1 equals 0.5. If proportion number 2 equals, my connection is unstable. Am I not breaking? Yeah, I think I'm breaking here. Am I not breaking, guys?
No, you're not.
Okay. I was saying that P1, if the first proportion is equal to 50%, you will say P1 equals this A1. You are not going to write A1 here. You will write that proportion or percentage or probability that is given, which is 0.5. P2, if it's equal to 10%, you will write 0.1. So this PK, this K denotes the last value or the last P. If you have 3 P's, where you see K, you will write 3, and then you will write 3 here as well. If they are 4, you will write 4. It means that we will expect to have P1, P2, P3, and P4. So this PK here denotes that they end at, actually, let me write this dot here to show that P2 up to PK. PK denotes the last value of P. If they are 100, you write P1 up to P100, and then you also write their values. I don't know if you understand. Do you?
Yes, we
Okay.
do.
Yes, I understand.
Okay. When it comes to H1 here, how did they arrive at this of saying at least one proportion, meaning that at least one of this is not equal to its specified value? So can I please go to another page? Yeah, this way of doing things is really challenging. What they mean by at least, remember at least means greater or equals to, meaning that more, one or more P is not equal to its specified value. Remember, if your H naught says P equals something, what do we expect from H1? H1 will say P is what?
Not equal to
Equal to.
Not equals to A. So that condition is derived from this. Remember, we have P1 equals H1, P2 equals A2, up to PK equals AK, right? So H1 will say P1 not equals to this, P2 not equals to A2, up to PK not equals to AK. So sometimes in this null, in this alternative, I mean to say, you may find out that one of them, of course, P1 is the one that is not equal to its A1, but this one and this one are equal to their specified values. But I don't want to confuse you here. So what you have to write there is that at least one PI is not equal to its specified value. So what I'm implying here is that if you check this, it's at least one, because one of these P's that you see here is not equal to its specified value, which is P1. So P1 is not equal to A1, but these other ones are equal to A1, their specified values. So as long as at least one, meaning that one or more of these proportions is not equal to its specified value, then we are having H1. That is where the condition is coming from. So you will always write for H1, at least one of those PIs is not equal to its specified value. In brackets, you write there is a change or there is a difference. Are we together?
No, can you please start over, like where you were doing an example?
Okay, I will explain this when we look at the example. Ne? So for now, just know that H0 will always say this and H1 will always say this. And then you have to know what you have to write in brackets, right? So I will clarify it when we look at an example. So this session is left with less than 9 minutes. So once it kicks you out, you'll be given 2 minutes to rejoin, and then we continue without wasting time. So what about the H0 and the H1 for the contingency table? Am I not breaking?
No, you're not.
Okay, thank you. So under the contingency table, the H0 will always say, and I'm saying always, ne? It will always state that the variables, let's say maybe 2 variables are statistically independent. It will always state that the variables in question are statistically independent. That will always be the null for contingency table technique. So in brackets, you will write that variable 1 does not affect variable 2. And then close the bracket. Variable 1 does not influence the outcome of the variable 2, or variable 1 does not affect variable 2. So that is what they mean when they say they are independent. If you and I are independent, it means that whatever I do does not affect you. So if the subjects you did in high school are independent of, or the course you are currently doing now is independent of the subject you did in high school, then it means that the subject you did in high school do not determine the course you are currently doing now. Do I make sense? That is what it means when we say 2 variables are statistically independent. It means that the outcome of another variable does not imply or does not influence the outcome of another variable in question. Are we together?
Yes.
Okay, so now give me H1. Looking at that statement, obviously you can come up with H1, and it will also always be like that. So H1, who can give it a try looking at H0? Because remember, H1 is the opposite of H0.
The 2 variables are not independent, so they affect each other.
Yes, you can say the 2 variables. Can I please write it on the next page? So remember, it's for the for the contingency table. It's H1 for contingency table. So it implies that the 2 variables are, you can say, are not statistically independent. If you write it like this, it will be correct. If you also say the 2 variables, I'm going to erase this. Did you write it?
Yes, you did.
Okay. You can also say, instead of saying they are not statistically independent, you can say they are statistically dependent, meaning that the outcome of one variable influences the outcome of another variable. It means that variable 1 affects the occurrence of variable 2, or variable 1 affects variable 2. Do you understand?
Yes, you do.
Okay. So that will be what we have to write in brackets, but you will be given the variables, the names of the variables. So you are not going to write 2 variables. So you will name them, you will specify them according to the question. You will see the example we are gonna do. So does it make sense up to so far? Can I move on to the third condition? Did you understand the H0 and the H1 for both the techniques?
Yes.
Yes, you did.
Okay, thank you so much. Let me go to the third technique. This is goodness of fit and contingency table. Goodness of fit and contingency table. So the third condition comes with the issue of calculating the expected frequency. The expected frequency is denoted by EI. The expected frequency is denoted by EI. And for goodness of fit, you are going to calculate it using NPI, where N denotes, EI denotes the expected frequency, N denotes the sample size, and PI denotes the proportion. EI is the expected frequency, N is the sample size, and PI is the proportion. This is the formula for finding the expected frequency for goodness of fit. For chi-square, I mean to say for contingency table, your EI will be given by RT times CT over N. Listen carefully here. EI denotes the expected frequency. RT, this R stands for rho, rho as in row, row. RT is the row total. T stands for total. And then CT stands for column total. And the N, obviously, it is the sample size. So we are going to calculate the expected frequency using the row total multiplied by the column total over the sample size. That is what you have to know. Do I make sense? And you can also write EIJ there, the expected value for IJ for a particular.
Sorry,